let's take it away. So this presentation is about comparing distributed memory frameworks, their performance and productivity with Radix sort. This is work done by Michael Ferguson, Matt Drozt, Ryan Fries at PNNL, and I. And let's get right into it. So in the world of HPC, often we focus on getting every last out of performance out of our applications, and we often rely on some sort of distributed memory programming framework to write our code. But oftentimes we let productivity take a backseat, except in HPC these days, we really need both the peace and the power of productivity and performance. So we want to explore a distributed memory programming framework that can deliver both. So how this study came to be was that we evaluated several different frameworks of this kind using a communication-intensive LSD Radix sort benchmark. We chose Radix sort because we didn't want it to be a toy program. We wanted it to be a real workload. And it has some nice patterns that can sort of expose the benefits or lack thereof of using a certain programming framework. The results are described in this paper that we submitted to PodTM, and the following slides are a summary of our key findings. So in this experiment, what we basically did was we investigated 5 different programming frameworks, both on an HPE Cray Supercomputing EX and an InfiniBand system. So we used Chapel, OpenSHMEM, Conveyors, MPI, and Lamellar. And with each framework, we implemented the communication-intensive algorithm, the LSD Radix sort. Michael walked through basically how that works. This is exactly the same pattern. Say if you have an array, and it's distributed across multiple locales. You have those locale boundaries on there. How do you sort that? You go, in this case, since it's the least significant digit first Radix sort, you by the least significant digit, you shuffle based on that, you got a new array, you can move on to the next most significant, and so on until you've gone through all of those, and then at the end, you've got the sorted array. You'll see that sometimes you have to cross locale boundaries for the shuffle step, and that's the communication intensive part, because more often than not, you will have to do that. Now, in this study, we had some constraints that we wanted to put. We wanted to have only 1 day of implementation effort per framework, and that was by an experienced developer, in most cases, Michael. This might sound a little arbitrary, but in most cases, it makes sense because the fastest application is the one that you can actually finish writing. So I think this is a good constraint to put that sort of enables you to also measure the productivity of a framework. We obviously had to tune each LSD sort under multiple runtime configurations to identify the optimal launch parameters for each of these frameworks. And we were using 128-bit key value pairs across varying data sizes and resource counts on the 2 different machines that we were running on. And the graph over here shows the minimum time to sort 2 to the 37 elements using 128 nodes on EX versus the lines of code in that implementation. So the closer to the origin you are on this graph, the better you're doing. So you can see that the simple fine-grained implementation is the fewest lines of code, but there are others that are doing slightly better in terms of performance. All right, moving on, here's sort of a similar view of it, but this table also includes IB sorting performance instead of just EX sorting performance, and it includes all the different versions. So you can see here, Chapel, the aggregated version performs best on EX as well as IB, whereas the MPI version is the most verbose, and unfortunately, OpenSHMEM, the simple fine-grained version, is not as good, nor in EX nor in IB. The numbers here are million elements sorted per second. An interesting observation you may have is that going from the Chapel simple fine-grained to the aggregated version added just 3 lines of code. And I think that's really great because adding those few lines makes your performance go up by like 60%, which is awesome. And you might want to learn more about how that happens. Even better on IB because on IB it goes like what, more than 10x, something like that. And this is because we use Chapel's communication aggregation features. So copy aggregation is a module that is inbuilt in Chapel that allows this. Now, why is the increase on IB so much better than the increase on EX? Because EX as an architecture is optimized for smaller messages. So it's already doing well even without COM aggregation, whereas IB needs that to get any performance out of it at all. All right, so the built-ins that we have, as I mentioned, with the copy aggregation module, really promote developer productivity. We saw a huge boost in the performance of our code, going from the simple fine-grained to the aggregated version. And over here, I'm going to show the few lines of code that we need to change. In this sort of big for all loop, which is the biggest, most communication-intensive step in the sorting process, what we do, well, obviously you have to add the copy aggregation module as a use statement. Outside of the for loop over here, we added an aggregator, which is the destination aggregator, which basically stores all the things that you want to put on a different locale. And as you go along, it's going to fill up that cache and then do one single com to sort of flush that cache at the end. And then in the for loop, we basically fill up that cache. So instead of doing this a pos equals temp I, we get rid of that and we use the aggregator dot copy function, which basically copies temp I into the pos index of the array A. And then at the end, we just flush out the aggregator. And that's all the changes that were made to the aggregated version to get the benefits of aggregated com. All right, and from here, I'm going to let Matt share with us how these best performance versions of each of the frameworks scale across the different frameworks. Matt, take it away.
Sure thing. Yeah, everyone's got to listen to my voice now, so that'll be fun. Yeah. So we saw some of those initial results that we or that Shreyas presented earlier in that kind of scatter plot. And indeed, in that table, those were measured at like a single point with a single amount of resources and a single, amount of data that was getting thrown at the problem. And we were recording those results. Of course, we want to make sure that one of the things that's important with an algorithm is that it be able to scale from, a very, very small problem size to a large problem size. Ideally, you shouldn't have to rewrite any of your code. One of the things that we want to do in this thing is indeed like quantify and qualify the productivity of each one of these libraries, frameworks, languages, etc. So that requires it be performant at a variety of scales. So just kind of like briefly touching on what we saw with some of these scaling results. We have some weak scaling results here presented for you all today. Weak scaling, of course, we're going to just increase the problem size. And as we increase the problem size, we're going to increase the number of resources that we're throwing at that problem at the same rate. Ideally, this means the amount of time it takes to solve the problem stays constant and the performance will grow linearly. Good news is that we saw all of these frameworks had like relatively good weak scaling. All of them were relatively like kind of flat. As we added more time and we added more data, the time stayed about the same. And indeed, the performance went up for all of them, which was good to note. We were happy as, related to the Chapel project as we are, that Chapel came out to be the most performant of the one once we made that aggregation change that Shreyas kind of touched up there. Yeah, and these and really what this kind of shows is that all of these frameworks are indeed able to like scale as you increase your problem size, which again, like we touched on, is good for productivity. If you're able to write something small and test it out, there's a good chance it's still going to be performant as the problem size grows. Yeah, kind of moving on from this, we wanted to like kind of expand out past our original least significant digit radix sorts. So we started looking for other sorting algorithms out there in the wild just to compare. The big one that we saw here was Chapel, of course, has a most significant digit radix sort that exists in the standard library, and we used a slightly simplified version of that to profile. I believe that is like a near direct copy of what Michael was describing in the last talk. And then we found this Cadus AMS sort. It's implemented in MPI. It was part of a doctoral thesis. I naively skimmed a paper, pretended to understand it, and then was told, yes, it works really good. So that is kind of the number, what I'm running on here in terms of description of, or how in depth I can describe that sort. As you can see here, we got a table, we got some numbers. These are great.
Oh.
I'm a particularly stupid man, though, and I prefer pictures. Good work, Shreyas. Move the slide on. Yeah, so here we got a more visual representation of the numbers that we were taking a look at. Indeed, in the previous two tables here, you can see already the first thing I want to call out is just that jump in performance going from that Chapel simple, fine-grained, and using the aggregators. This is just one of the nice things about Chapel. Again, not to turn this into an advertising thing for Chapel, but it's ChapelCon, so I'm going to do that. A lot of these things for these easy wins for performance are kind of like built in naively into or built into the language, allowing developers to have that kind of ability to write and then very, very minimally tweak in order to get these better performance numbers. Again, another thing that we want to call out is Chapel is best in terms of performance, beating out MPI, which tends to be kind of the industry standard, and then indeed OpenSHMEM, which is this other framework. And we are able to see that OpenSHMEM also is able to increase its performance by adding on Conveyors, this library framework language extension thing, call it what you will, by doing something similar to what Chapel does, which was add in some level of aggregation for communication across the ranks. And if we take a look at the lines below the dashed the
Sorry.
bars. Yeah, you're good. Don't worry. Bars below the dashed line there. These are the more complex sorts that we see. And we see the Chapel is coming on very, very impressively with times or a performance like very similar to that doctoral thesis implementation of that sorting algorithm. But what I think is like particularly interesting is if we move on to the next slide. Go ahead and jump now. This scatter plot is an extension of the one that we saw earlier in the slide. If you take a look at everything there, where the lines of code is less than 500, that is the scatter plot that we saw earlier in this performance, and we can see how this kind of stacks up. But what we take a look at here is these two new points, that Cadis sort and the Chapel standard library implementation most significant digit Radix sort. We can see here that they have a slightly lower time, e.g. a higher performance, and unfortunately much larger number of lines of code. But what is super, super interesting is that, again, at least in my opinion, is the Chapel performance or the Chapel implementation of the most significant digit Radix sort is nearly as performant as the Cadis implementation, but it's like particularly like there's significantly fewer lines of code, which is an imperfect analogy to like kind of developer productivity. There's more that can be expressed in a single statement in Chapel than there is in a raw C MPI implementation. Again, it's an imperfect metric, but this is a way that we were able to like quantify productivity. And if we move on to the next slide, I believe this week we can get to some more of our qualitative findings regarding some of these frameworks. I'm just going to try and speed this up just a little bit. But yeah, these are things that we couldn't like strictly measure or report numbers on, but this is just kind of our experience having used these frameworks. MPI, of course, is the industry standard, but some of the biggest problems that we have with it is that it's missing a lot of just these niceties that you can find in these other frameworks, more complex data types, etc. You tend to be casting a lot of bytes around. And you can introduce these weird conditions where the best thing, the standard advice for MPI applications may not necessarily give you the best performance. We found that running with less than one rank per node was actually more performance. Usually you're running at about one rank to a node or one rank to a core or whatever. Chapel, of course, we love it. It was very concise. It's got a lot of these things, like I said, kind of built in for these easy wins in terms of performance. The documentation is there. It's great. It's lovely. But we do have some kind of long compile times, which of course can like slow developer iteration. It's something that is known and actively being worked on though. OpenSHMEM, very easy to install, very fast to compile. It's very C. Cons is kind of similar to MPI. It uses a custom collective allocator, which means that it was very difficult to integrate with native C++ data types. Yeah, sorry, I just saw the chat. Hard to, and this wasn't just something where we could use a custom allocator within C++ for these data types. It was very like ingrained into the system. So it was not easy to work around. This, of course, because it doesn't like map and forth easily with C++, it's not fantastic to work with, at least in terms of like a developer ergonomic standpoint. And then, of course, the addition of another framework library, et cetera, whatever you want to call it, Conveyors on top of it in order to get these things is kind of a pain and requires a good amount of rewriting in order to get like the kind of performance that we saw with a 3-line change in terms of Chapel. Lamellar is very cool. It's definitely the most up and coming on this list. So, you know, it's harder for us to like fully explain our experience about this because none of us are Rust developers by trade. This is a framework that is designed for Rust, but from what we saw so far, it looked very nice. It feels very familiar to other frameworks, at least as far as we can tell. Again, we're not Rust developers, like first and foremost. But it does come with a lot of the benefits that come with Rust projects. In that it had some very nice error messages. It was very easy to debug, very good at catching things at compile time. Unfortunately, it also came with a lot of the drawbacks that come of Rust projects, particularly, again, compile times. And then, of course, it only is currently available on IB systems. Again, new and up-and-coming project. It's definitely one to keep the eye on, and we are excited for its future. So yeah, last little bit here that we're going to talk about is this we want to like try and keep alive. We know we sent Michael out on this massive quest to like try and investigate all these frameworks and see what he can do. Michael is only human, unfortunately, though, so we're certain that we didn't like absolutely make this as best as possible. We have published our results or have our results published and presented here as far as we are aware. These are like the best performance numbers that we could come up with. But if you think that you can come up with something better, if you have more experience in any single one of these frameworks, we highly encourage you to please take a look at what we did and tell us what we did wrong. I believe somebody pointed out the best way to get audience participation is not to present cool and good and correct things, but to present things that are wrong so that you can tell us that we're dumb and stupid and you found the fix. Good work. We have a link here to our repository. Please, we encourage everyone here to take a look. But outside of that, this is kind of our very, very high level look at our findings. I think this gives us just a little bit of time for questions. If anyone has anything for either me or Shreyas, please go ahead, speak up.
Thanks. Let's give our speakers a round of applause. And Daniel, jump in with a question.
All right, I have two, but I for now only remember one. And this is gonna like identify me as someone who isn't very familiar with like actually writing performant parallel code. But you mentioned about how adding aggregators improves the performance of your programs. And I was just wondering, so in this bucketing thing, right? Because what you're doing is just creating buckets in a new like next generation array or something like that. Do you really need to wait for the result of your writes to go through to continue? So like, I understand that small individual writes are slow, maybe because you have to go through the network. But if you just fire them off asynchronously in a non-blocking manner, it seems to me like it like oughtn't matter as much unless you create congestion. What am I missing that kind of makes these write and forget patterns still expensive despite the fact that you're not reading the data back?
Trace, would you like me to answer this question?
Yeah, sure. You can take it away, Michael. I'll just bring up this slide.
So Daniel, there's the first thing is those write and forget patterns. The fact that you don't care about the result going in any particular order is what allows us to use an aggregator without changing the algorithm. The second thing is that actually Chapel has the cache for remote data enabled by default, which does make use of you can sort of save things away and then send them in a more bulk way. But if you're doing random access, that kind of caching approach doesn't help that much, although it can change things from blocking writes to non-blocking ones, and that can give performance on some networks. So your intuition is right. It's just that the default semantics in Chapel don't make use of that, because how would the compiler know that you're not going to use it again? So we have compiler optimizations that turn on the aggregator when it can figure that out, if you ask for them, or you can use it manually like this to indicate it's okay.
Thanks very much. That makes sense. I have another question unrelated to this, unless someone else wants to jump in.
Go for it.
Alrighty. So You had this plot of performance versus lines of code, a couple of these plots, right? The small one and the big one.
Correct.
And this reminds me of the computer language benchmarks game where we plot a whole bunch of different languages on various benchmarks in a similar manner, where we have like time and lines of code. There, however, we gzip the implementations to kind of, I guess maybe strip out more of the dependence of like the length of the syntax or maybe like the verbosity or like not even the verbosity, but just like the high level irrelevant details of like how you write things. Have you tried using gzip on these? And if you have, has that affected your results at all?
I should have explained how we got these measurements for lines of code a little bit. Yes, we did not use gzip or anything like that and actually try and compare sizes that way, but we did default to like a standard tool in kind of the ecosystem clock for counting lines of code. It will count lines of code in a standard manner, and then we tried to just strip out anything that was unnecessary or irrelevant to like the immediate implementation. So any kind of like int main, type details, any of that any kind of imports or includes or usings or whatever, stripped those out. And we tried to keep it like just using clock, measure the critical section of each one of these sorting implementations, just to keep it to like the pieces of code that actually matter. So in a long and roundabout solution, no, we did not do any kind of like gzipping or anything like that, but we did try and keep our counting of lines of code relatively standard
That
or
makes sense to me.
standardized. Yeah.
Though I still wonder if like Chapel has some advantage in that, if you're a C++ programmer, you probably use curly braces for your conditions. Whereas Chapel, you can use like say a do block, which technically shaves off one line for the curly brace, right? And
Sure.
for that kind of thing that I don't consider particularly relevant to the productivity or like, conciseness of a language, but would get picked up by clock because it's a non-empty, non-comment line.
Of course, yeah.
But yeah, I mean, using clock is definitely a very robust way to rule out, comments and irrelevant things.
Exactly, yeah.
Yeah, the key thing is that none of these implementations are playing code golf. So they're all, more or less on a level in terms of complexity per line.
Thanks.